The drive to reduce harmful vehicle emissions and improve fuel efficiency continues around the world. This has led to significant changes in vehicle engine technology. Utilizing a lower viscosity grade engine lubricant is now widely known to deliver improved fuel economy and reduced greenhouse gases. A typical way of measuring the viscosity of an engine lubricant is kinematic viscosity, derived from the time it takes for a fixed volume of liquid to flow through a tube under the force of gravity. So let's look at what the two numbers mean. The second part in the SAE J300 viscosity classification relates to how long an oil takes to flow through a tube at 100 degrees Celsius, representative of normal operating temperatures. As well as knowing how an engine lubricant is going to perform when it is hot, we also need to consider the physical properties of the lubricant when it is cold. So this is where the first number comes in. Here we have two viscosity grade engine lubricants, a SAE 15W40 and 5W30 at a temperature of -30 degrees Celsius, simulating extreme cold startup conditions. We can see the higher viscosity oil on the left is taking significantly longer to flow than the lower viscosity grade oil, which will flow around the engine much quicker, helping protect key engine components during this critical startup time. But is this the full story for efficiency? Let's look at two engine lubricants with the same viscosity grade, in this instance SAE 5W30. They both look the same, they both are flowing the same, but one is actually more efficient than the other. Let us take a closer look. During an engine's operation, the lubricant is exposed to more than just gravity. The lubricant is required to lubricate and protect areas such as the bearings, camshaft, piston rings and liners under high shear conditions at high temperatures. Here the first 5W30 engine lubricant squeezes through the moving parts. Protection of components is maintained, but the resistance to flow of the oil means the engine needs to generate more power to maintain performance. This leads to more fuel being consumed. Again, the second lubricant squeezes through the moving parts. Protection of components is still maintained, but the resistance to flow of the oil is less, meaning the engine needs to generate less power to maintain performance, and so less fuel is being consumed. This is obviously good news for the vehicle owner, and is good news for the environment. So coming back to the two engine lubricants we saw earlier, what was the difference between the two? Even though they are the same viscosity grade engine lubricants, the first one has what is called a higher HTHS viscosity than the even more efficient engine lubricant on the right, which has a lower HTHS viscosity. High temperature, high shear, or HTHS dynamic viscosity, is the current industry standard test that best predicts fluid behavior in the operating conditions of an engine. HTHS measures the temporary viscosity loss of an engine lubricant under high shear at elevated temperatures. The lower the measured number, the lower the HTHS viscosity of the engine lubricant, and the higher the predicted fuel efficiency benefits the end user can expect. Original equipment manufacturers are moving to lower HTHS viscosity engine lubricants for their latest engine hardware in order to achieve lower greenhouse gas emissions and increased fuel efficiency of their vehicles. Engine lubricants are complex fluids, and low HTHS viscosity lubricants require formulation changes over high HTHS viscosity lubricants. It is essential lubricants are correctly formulated, and Lubrizol has many years of proven experience developing low HTHS viscosity formulations using innovative performance additives and performance polymers, delivering fuel efficiency improvements whilst maintaining durability and protection, keeping the wheels turning for today's requirements and leading the way for all of those still to come.